Hello, welcome. Yes, I'm going to talk about diffuse decompositions of polynomials, which is a theory that I developed a few years ago. So an overview of what I'm going to talk about. I'm going to give an introduction where I'll talk about polynomial threshold functions and some of the questions relating to them, which will be sort of the main application of this theory. I'll then talk about the invariance principle and the replacement method, which is sort of an important technique in this field for proving a number of things. I'll then, after sort of going over how this technique works in some detail, talk about where the bottlenecks lie in the existing techniques. And from there, I'll talk a little bit about what we might try to do to get around these bottlenecks. This leads us to sort of the meat of the talk, the actual discussion of this theory of diffuse decompositions. From there, I'll talk about how to use this theory to prove a better version of the invariance principle. And then I'll give a brief application to the noise sensitivity of polynomial threshold functions. So we'll start with some basic definitions. We say that a function from Rn to R is a degree d polynomial threshold function if it's of the form f of x is sine of p of x, where p is a polynomial of degree d and n variables. So you take an x, you evaluate this polynomial at it, and then you return plus or minus 1, depending on whether the result was positive or negative. So what we're going to be interested in are questions involving the sort of related to the evaluation of polynomial threshold functions at random inputs. And these inputs will be either from the n-dimensional Gaussian distribution or the n-dimensional Bernoulli distribution. So every coordinate independently and randomly plus minus 1 with equal probability. Because of this, we'll be caring about what polynomials do at these various inputs. It's nice to have some idea of the size of a polynomial. So we'll be making extensive use of the LT norms of the polynomials with respect to these distributions, and in particular the L2 norm. And so in particular, we just recall if you have your function from Rn to R, then you define the LT norm with respect to either the Gaussian or Bernoulli distribution to just be the 1 over tth power of the tth moment with respect to this distribution. Okay, so when we're studying these types of questions, you can find that many of these questions that we want to ask about polynomial threshold functions are easier to answer in the Gaussian case. And this is for a number of reasons. For one reason, the Gaussian distribution is far more symmetric than the Bernoulli distribution. And there are several instances in which you can take advantage of this symmetry to get very clean proofs of some results. And additionally, the Gaussian distribution is continuous, whereas the Bernoulli distribution is not. And this gives you a lot more analytic tools that you can bring to bear on some of your problems. On the other hand, many of the questions are more interesting in the Bernoulli case. And this is, again, for a few reasons. One is just that a lot of these questions show up in theoretical computer science, where, of course, people tend to be interested in functions with discrete inputs and discrete outputs, rather than these continuous Gaussian inputs. Secondly, the Bernoulli case is often just strictly more general. The central limit theorem tells us that we can think of our Gaussians as just sort of some average of a giant number of independent Bernoulli random variables. And often by sort of making this approximation, there's an immediate reduction from the Gaussian case to the Bernoulli case. And additionally, because of this discreteness, the Bernoulli case has some sort of, the polynomials have a bit more structure to them than you would see in the Gaussian case. Now, because of this state of affairs, it would be nice if we could reduce questions corresponding to questions in the Bernoulli case to questions about the Gaussian case. And, well, one way to do this is what's known as an invariance principle. An invariance principle is a theorem that shows that for certain multilinear polynomials, that the distribution of p evaluated at a Gaussian is approximately the distribution of p evaluated at a Bernoulli. And usually the similarity is in something like in terms of the cumulative density functions. Of course, you can use some other metrics as well. Of course, they won't be close in statistical distance because the first of these distributions is continuous and the second one's discrete, so the statistical distance will always be 1. But in some of these other metrics, they might still be close. So in particular, if you think about this for degree 1 polynomials, this reduces to a special case of the Bernoulli theorem. It says that if you look at a linear combination of independent Bernoulli random variables, then in terms of the cumulative density function, this thing will be close to a linear combination of the same linear combination, in fact, of independent Gaussians. But of course, this linear combination of independent Gaussians is just the single Gaussian with the correct mean and standard deviation. So the major technique used for proving these sorts of results and a number of other results is known as the replacement method. This is actually a pretty general technique for proving approximations of the following form. You want to show that the expectation of f at x1 through xn is approximately the expectation of f at y1 through yn, where here f is some function. In this case, it's the polynomial threshold function. The xi and the yi are independent random variables such that the low degree moments of xi agree with the corresponding moments of the yi. And this technique is used to prove a number of things, including invariance principles, as we'll see. It's also used to prove error bounds for a number of different pseudo-random generators. We can also see later there are applications to bounds on noise sensitivity. So what's the basic setup here? The first step is going to be that we want to take this function f, which generally is going to be this sort of threshold function type thing, and we're going to want to approximate it by a smooth function g. And we'll see a little bit later why having a smooth function is useful, but for now, once we do this, we sort of now want to prove the following sequence of approximation results. We want to show that the expectation of f of x is approximately the expectation of g of x, which is approximately the expectation of g of y, which is approximately the expectation of f of y. Now, for sort of technical reasons, it will often be the case that the last of these approximations is hard. And so to avoid actually proving this last of the approximations directly, we'll actually sandwich f between two smooth functions, g plus and g minus. So then once we have the first three approximations, we have the expectation of f of x is approximately the expectation of g plus or minus of y. We can sandwich the value of f of y between those and sort of get around having to prove the last thing. So in practice, we'll always be using sandwiching functions, but for simplicity in the analysis that we'll be giving, we'll just assume that we can pick an approximation and just show the first two of these steps. Okay, so we've replaced f by a smooth function g. What does that gain us? We still need to show that the expectation of g of x is approximately the expectation of g of y. Now, so the key idea here is that we're going to show this by replacing the xi by the corresponding yi one at a time. And so the point is we want to show that the expectation of g, when we evaluate it at y1 through yi minus 1 and yi, and then xi plus 1 through xn, that should be approximately the expectation of g evaluated at y1 through yi minus 1, and then xi instead of yi, and then xi plus 1 through xn. So the idea here is that because our x's and y's are all independent of each other, we can sort of fix the values of y1 through yi minus 1 and xi plus 1 through xn. And then because g is smooth, we can Taylor expand it about this ith coordinate. So we get that g, if we call this ith coordinate z, then g of y1 through y minus 1 and z and then xi plus 1 through xn is some polynomial a0 plus a1z plus etc. plus some error term. And the point here is that we want to evaluate this thing. We want to evaluate the expectation setting z equal to xi or z equal to yi. But the point is that by assumption, those guys have their moments agree, to the small order moments agree at least. And so this means that when we take the expectations of the first few terms of this Taylor expansion with either z equals xi or z equals yi, we get exactly the same thing. And thus the only difference in these expectations comes from the higher degree terms in this Taylor expansion. And so roughly what happens is if the first k moments of xi agree with the first k moments of yi, then the first k terms in the Taylor polynomial wash out, and then you have an error term that's roughly the size of the k plus first derivative of g with respect to this ith coordinate.
So inherently in this kind of hybrid argument, you will lose a factor of n because you're adding up.
Yeah. You'll then have to sort of multiply this thing by n, or more precisely, you'll have to sum it over all n coordinates. But this doesn't necessarily lose you so much. There are cases where you can get essentially tight, like you can get actually the correct bounds on it by using this sort of analysis. But you do then need to sum this result over all coordinates.
You know,
Yes, there's a dependence on k. And so that means that if xi and yi agree to higher order, you sort of agree to higher order moments, you can often end up with a better final result. Okay, so that's what we would do if we had a smooth function. But of course, our original function isn't smooth, so we need to show that if we replace it by a smooth function, we don't lose so much. So we want to show that the expectation of f of x is approximately the expectation of g of x. And to do this, we're just going to show that with high probability, f of x is approximately equal to g of x. And this generally amounts to proving some sort of anti-concentration result. That's a result that tells us that x, or that some function of x, has only a small probability of lying in a small neighborhood. And the point here is that often when we're applying this, f is some sort of threshold function, and so it's discontinuous. And if we're trying to approximate a discontinuous function by a smooth function or a continuous function, of course, we'll have a large discrepancy somewhere near the locus of discontinuity. And what this means, therefore, is that if we want to show that f of x and g of x agree with high probability, we need to show that there's only a small probability that x lies in this whatever neighborhood of this locus of discontinuity we have, where there's actually a large error between them. So we need some sort of an anti-concentration result. Okay, so this is how the replacement method works. Let's see how we can actually use it to prove an invariance principle. So the idea here is we have f of x is sine of p of x. It's the threshold function. We've got p a normalized polynomial, say with variance equal to 1. P is multilinear, meaning it doesn't have any higher degree terms in terms of any single variable. Xi is a Gaussian random variable, yi a Bernoulli random variable. They agree to their first three moments. And what we want to do is we want to show that the expectation of f at x1 through xn is approximately the expectation of f at y1 through yn. And what? F should be degree d, which ends up being used later. Yep. And the point is that this sort of relates the probability that p of x is bigger than 0 to the probability that p of y is bigger than 0, which is sort of exactly the type of thing we need if we want to show small error in terms of the cumulative density functions. So the first thing that we need to do for the replacement method is approximate f by a smooth function. And there's sort of one obvious way to do this. We let g of x be rho of p of x, where rho is a smooth approximation to the sine function. So here, let's say rho of x is equal to sine of x whenever the absolute value of x is bigger than some parameter eta that we'll figure out later. Well, I mean, it's equal to sine of x outside of that neighborhood. Okay, so we've got two sorts of errors to deal with. We have the error from actually running this replacement, and this is roughly on the order of the sum of I is 1 to n of the expected fourth partial derivative of this function g. And next we have the approximation error, which is roughly the expected absolute difference between f of x and g of x. So starting with the replacement error, we want the fourth partial derivatives of g. Well, g is rho composed with p. P is multilinear. So these are just the fourth derivatives of rho times the sum of the expected fourth powers of the first partial derivatives of p. Now, rho changes from being constant plus 1 to constant minus 1 over a distance of size about eta. So that means its fourth derivative is always going to be about eta to the minus 4. And so we've got this eta to the minus 4 times the expected sum of fourth powers of the partial derivatives of our polynomial p. So of course, this last term depends on our polynomial, and of course, we expect the error to depend somewhat on our polynomial, but we want some terminology in order to get a handle on how big this is. So a convenient way to talk about this is by defining the influence of a polynomial with respect to a coordinate. So at least for multilinear polynomials p, we define the ith influence of p to be the expected square of the ith partial derivative of the polynomial. And this isn't quite the standard definition of influence, but at least for multilinear polynomials, it turns out to be the same. One useful... What? Rho is just some smooth function that agrees with sine of x away from 0 and interpolates it somehow nearby. And in particular interpolates it between eta and minus eta. Yeah, I mean, so, I mean, the reason why we have an eta to the minus 4 is that... Yeah. 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 Okay, so we're getting our hands on this using these influences. One convenient fact to note, and which isn't hard to prove, is that if you have a polynomial of fixed degree, the sum of all of the influences is on the same order of magnitude as the variance of the polynomial.
So that's a good time to ask you, all these reasons will be up to exponentially the degree?
Well, I think this one is linear. There will definitely be exponentials in the degree cropping up at some point. I'm not sure if they've cropped up yet. Sure. Well, certainly on this next line, there is an exponential in the degree being hidden here. So the idea is that we have this replacement error. And it was the sum of the fourth powers times eta to the minus 4. Now that's roughly the sum of the squares of the influences. And now I'm actually hiding an exponential term in terms of the degree. Since I assume that the variance, which is roughly the sum of the influences, was 1, this sum of the squares of the influences, at least I can bound it in terms of the maximum of the influences. So I've... let's see. I mean, all of these terms that I'm doing, since all the polynomials that I'm writing down are multilinear. Oh, I guess when I'm taking fourth powers, it could matter. Let's see. Yeah, I am using hypercontractivity in here. Everything that I'm saying should hold in either the Gaussian or the Bernoulli setting. If I actually want to be applying this for the replacement method, I actually need to use a mixed setting, because when I'm replacing the ith coordinate, I need to consider it where all of the coordinates before the ith coordinate are Bernoulli and all the ones after it are Gaussian. But the point is that the hypercontractivity, which is the only real difficult thing that I'm using, holds in both settings, so it also holds in this mixed setting. So yeah, I'm sloughing a little bit under the rug there. No, I mean, literally, like the second thing there, it's just a strict upper bound, more or less. It, in fact, could be better than that, but this is good enough for us. So we have a bound on the replacement error in terms of this parameter eta and the maximum of the influences. And it actually makes sense that we want an error bound in terms of the maximum of the influences. Because if you had some single coordinate with a very high influence... Yeah, I wrote it back on the last slide. Yeah, last slide, yes. I assume that the variance was 1. Yeah, sorry. So the point here is that it makes sense to bound things in terms of the maximum of the influences. If I have some variable with a very large influence, then it means that the value of my polynomial depends very much on the value of that one variable, which would make you suspect that the distribution of my output should depend a lot on whether that one coordinate is Gaussian or Bernoulli. So you expect that if an influence is very high, then you should actually have a large error when trying to run the replacement method. Well, I mean, your invariance principle, you expect to actually have a large error. So this is a very reasonable thing to bound in terms of. So what we're going to do is we're going to make a definition. We're going to say that a polynomial is tau regular if all of the influences are less than tau times the variance for all I. And this is, of course, with our variance normalized to 1, this is just the tau that works is the maximum of the influences. Okay, so that was the replacement error, and now I need to look at the approximation error. This is, of course, the expected absolute difference between f of x and g of x. Now, f of x and g of x, remember, g of x is rho of p of x, and this agrees with sine of p of x unless p of x is smaller in absolute value than eta. So this is roughly the probability that the absolute value of p of x is less than eta. So as I said, we need some anti-concentration result. We need to know that the probability that p of x lies in a small neighborhood isn't too big. And fortunately for us, we have the following lemma of Carberry and Wright, which says that if p is a degree d polynomial, x is a random n-dimensional Gaussian, and epsilon is some parameter bigger than 0, then the probability that the absolute value of p of x is less than epsilon times the L2 norm of p is O of d times epsilon to the 1 over d. So at least what this tells us is that if eta is sufficiently small, then this probability can be made as small as we like. So this means that we have an error that's on the order of eta to the 1 over d. And, well, so basically now all we have to do is put everything that we've said together. We adjust eta to minimize the sum of the replacement error and the approximation error, and we get out more or less the following invariance principle of Mosel, O'Donnell, and Leskovich, which says that if p is a tau regular, degree d multilinear polynomial, then the CDF distance between p at a Bernoulli and p at a Gaussian is O of d times tau to the 1 over 8d. So this is a great result. It's had many applications, and it's very convenient. I mean, the tau to the 1 over 8d is not great if the degree of our polynomial starts becoming reasonably large, but at least it tells us that if we have a highly regular polynomial of whatever degree we want, we have a small CDF error.
You never said what the rho was. You never needed any property of the rho.
I mean,
Around eta,
sure. We need some property of the rho. Basically, we need that its fourth derivative is universally bounded by some constant times eta to the minus 4. And so as long as that holds, then it doesn't matter what it is. Yeah. So we probably also want it bounded between minus 1 and 1. And if we're actually doing this with the sandwiching business, then we also are going to actually need two different rows, one of which upper bounds sign and the other of which lower bounds it. But none of that's very difficult. Any more questions before we move on? Okay, so now the invariance principle straight up, it has a number of useful applications, but a lot of the applications you want to prove things about general polynomials, and of course not all polynomials are regular. And so in a lot of cases you can't just immediately use the invariance principle because if you're not regular you're not going to have any reasonable sort of error anyway, and you need some way to be able to work with them. Now, on the other hand, one suspects that if you've got an irregular polynomial, it's not for some really deep reason. If a polynomial isn't irregular, it's because you have some very influential coordinate. And in fact, because the sum of the influences is on the order of the variance, you can't have too many influential coordinates because you have some small number of highly influential coordinates. So to get around this irregularity, there's this basic idea that what you can do is you can take these few influential coordinates and sort of deal with them separately. And the idea is that if you sort of fix the values of these influential coordinates, once you've conditioned on what their values are, you expect one of two things to happen. On the first hand, it could be the case that your polynomial is essentially just a polynomial in a couple of variables, and that once you fix the values of these coordinates, you've essentially determined the value of the polynomial up to maybe some very small error. On the other hand, it could be that you've got some nice regular polynomial, and you just have added to it some couple of coordinates that now have very high influence. And if you're in this latter case, you expect that once you've sort of conditioned out on the values of those coordinates and sort of thrown them away, you then have a regular polynomial and can use the invariance principle. So the idea is that in either case, you can sort of either reduce to a trivial case or reduce to the regular case, and such theorems have shown up in a number of contexts. They've come to be known as regularity lemmas. So as I've said, a number of different regularity lemmas have showed up in the literature over the years, and the following one is not quite one that I think has ever been formally stated in a paper, but it sort of is along the same lines, and it's more comparable to stuff that I'm going to talk about later. So the theorem says basically the following. If p is a degree d polynomial and tau is bigger than 0 as some parameter, then, well, I'm going to want to sort of fix these high influence coordinates, but unfortunately I can't just pick the coordinates that I'm going to fix and then fix them. That sort of technology doesn't exist to do that. I might have to fix a few coordinates and then based on the values that I got back from those coordinates, figure out what coordinates I want to fix next. Well, yes. I think it should be the case that you can write it should hold that there is a regularity lemma where you sort of don't have to do this adaptively, where you can just up front pick a bunch of coordinates, fix them randomly, and then everything that I'm saying should hold. But I think that that's true. No. So it can be done in terms of the cost of making the depth exponential. I think that it can be done without affecting the depth very much, but I don't know how to prove it. Okay, sure. Yes, you're right. You might be forced to have a 2 to the d coming out if you do this non-adaptively. But this result already has a 2 to the d in it. So, in any case, so the point is that what we're going to do is we're going to write p as being equivalent to a decision tree of some depth, which is about tau inverse here, assuming that we're taking the tau as small limit. And what's going to happen is, well, the leaves of the decision tree, of course, are going to be new polynomials. But it's going to be the case that with probability of at least 1 minus tau over a random leaf, one of two things will happen for this resulting polynomial. Either it will be the case that, say, the variance of this polynomial is less than tau squared times the squared L2 norm. And what this means is that the polynomial is actually defined up to a small relative error. And so, meaning it's the value of the polynomial that we get out is nearly constant. And the second case, of course, is that your polynomial is tau regular. So you restrict, you end up with a polynomial that's either nearly constant or tau regular. This is all Bernoulli. So the point is that in a lot of applications, what we want to do is we want not just an invariance principle or a regularity lemma. What we really care about in a lot of applications is the combination of the two. Where here what we have is that if you have any multilinear polynomial that you want to evaluate at Bernoulli random inputs, you can always write it as a decision tree of depth about tau inverse, where the leaves with probability 1 minus tau give you polynomials that are either nearly constant or close, by which I mean O of d times tau to the 1 over 8d within CDF distance of some polynomial evaluated at Gaussian inputs. So, okay, so this is useful, but as it turns out, each of the invariance principle and the regularity lemma that I've used here, they're individually essentially tight. You can't make massive improvements on the bounds, but this combination of the two is not. As we'll see later, you can actually get sort of, if all you care about is fixing some coordinates and then getting something that's close in CDF distance, you can do much better than this tau to the 1 over 8d. But it's going to depend on sort of finding a better notion of regularity. Because when you're going through this notion of regularity, both of the two halves of the argument are actually tight. So in order to sort of see where the problem lies, let's talk about a bad case for the invariance principle. And in particular, I'll show you that this tau to the 1 over d type dependence that we've seen is actually necessary. So the point is, let's take the polynomial p of x, which is tau times x naught, plus this other big linear term to the d, for d an even number. Now, the first thing to note is that this thing is not actually a multilinear polynomial. Because d is at least 2, the second term is going to have terms in it with the higher powers of a given variable. On the other hand, as long as n is large, there's a pretty easy way to replace this by a multilinear polynomial for which everything I'm about to say is still effectively true. So one thing to note here is that p here is roughly tau squared regular. because the influence of the first coordinate is tau squared, the influences of all the other coordinates are small, and the variance of this thing is on the order of 1. On the other hand, when you evaluate this thing at a random Bernoulli, you always get at least minus tau with probability 1, because x naught's at least minus 1, and the second term, while we're raising it to an even power, it's always non-negative. On the other hand, when we evaluate this thing at a random Gaussian, there's a reasonable probability that we get an answer that's less than minus tau. For example, there's a constant probability that x naught is less than minus 2, and then this other term becomes just an independent Gaussian raised to the dth power. If that Gaussian is less than tau to the 1 over d, which happens with probability about tau to the 1 over d, then the second term is at most tau. So the probability that p of a Gaussian is less than minus tau is on the order of tau to the 1 over d. And so we have a discrepancy between the CDF at a Bernoulli and the CDF at a Gaussian on the order of tau to the 1 over d. So the point here is that even though x naught is not very influential, it can actually have a very large effect on the distribution of our polynomial when the sum of the other variables is very small. And somehow its effect on the cumulative density function isn't properly recorded just by looking at its influence. So in particular, these problems sort of arise when you have poor anti-concentration in your polynomials. If the probability distribution of p of x is very highly clumped, then it means that sort of small errors in the actual value can lead to much larger errors in the cumulative density function. And in particular, this epsilon to the 1 over d dependence that we saw in Carberry-Wright is actually a major bottleneck. In fact, I mean, we saw this dependence show up exactly in our analysis using the anti-concentration method, and somehow this sort of problem is exactly what is preventing us from proving a better invariance principle. And so what we'd like to do, ideally, is just replace Carberry-Wright with something better. And heuristically, it makes sense that the probability that the absolute value of p of x is less than epsilon times the size of p should actually, morally, it should be on the order of epsilon, because we're asking for the probability that we lie in an epsilon neighborhood. Of course, this isn't true for polynomials in general. About the worst case that you can take is, say, x1 to the d, because then, as long as x1 is less than epsilon, x1 to the d is less than epsilon to the d. But you can have other sorts of problems. You could take x1 to the d plus x2 to the d plus x3 to the d plus, say, a small error delta. Then as long as x1, x2, and x3 are, say, all of size epsilon, this thing is of size epsilon to the d or delta, whichever one's smaller. And you can have more complicated counterexamples. You could have, some other polynomials, q1 and q2, which you raise to large powers and multiply together and stuff. And then you can still add a small error on the end. And even this polynomial, you can reasonably expect that as long as q1 and q2 are reasonably small, this third polynomial will be quite small. And it will be small enough with high enough probability to sort of break this heuristic version of anti-concentration. On the other hand, in all of the above, our polynomial p of x is failing to be as well anti-concentrated as we like, because there's some way that we're able to write it in terms of other polynomials. And it's sort of this decomposition that's causing anti-concentration to fail. On the other hand, this is somehow good news, that it's failing because of these decompositions. And the point is that the fact that we would have these decompositions should allow us to get around some of these problems that we were seeing before. For example, the point is that this first polynomial, if you take the dth power of a linear polynomial, well, now sort of running the replacement method with that leads to these sorts of problems because our polynomial isn't well anti-concentrated. But if you look at any threshold function of x1 to the d, those are just the threshold functions of x1, more or less. x1 is a perfectly well-behaved function. So if instead of looking at the dth powers of these guys, we just look at the original polynomials, we should be in much better shape. Yes?
Could you go backwards time?
A full slide?
Right.
Backwards to where?
One slide. To the left side.
Okay.
Yeah. So why in this, if you
Uh-huh.
Why did you need the second term anyway? I mean, won't be just tau times x0 or 2?
Well, if we just had tau times x0, this wouldn't be a regular polynomial
Oh, I see.
because the variance would be much smaller. Okay, so the point is that, well, if we actually have these sorts of decompositions, we can hope to get around these problems in the replacement method by sort of letting this function g, this smooth approximation, depend on the polynomials that we are decomposing into, rather than the original polynomial. Sort of the point is that when we were running our standard replacement method on the dth power of a linear polynomial, the fact that we had the dth power of the polynomial and we were having our g depend on this dth power of a polynomial, which has sort of this poor analytic properties, that was what was causing us to fail. If we have it depend on just the linear polynomial, we should be fine. Okay, so our basic idea is the following. For any polynomial p, we would like to be able to explain its failure to be as well anti-concentrated as we would like by expressing it in terms of some other polynomials that themselves don't have any sort of special distributional properties, and in particular don't have any bad anti-concentration properties. Now, in order to make all of this rigorous, of course, we need to introduce some terminology to sort of define what we mean here. The first thing is we say that if p of x is a degree d polynomial, we say that we have a decomposition of p of size m if we have a sequence of polynomials, h and q1 through qm, such that, well, the main thing is that p of x is equal to h of q1 of x, q2 of x through qm of x. So we've written p of x as some polynomial in these other polynomials. And secondly, I'm going to assume some sort of technical condition on the degrees of the polynomials, which basically says that we didn't write down really high degree polynomials and then have the high degree stuff all cancel out. So
there is no, so these are the degrees of the monomials of H, and what are
well, I mean, so basically what I'm saying is that if we sort of write out this formula, p of x is h of q1, q2, q3, qm, and expand it out, I want it to be the case that when we expand this out, we never wrote down any term of degree more than d. And this is just sort of the rigorous way of saying it. Yeah. Yep.
So you just didn't get lucky cancellation?
Yeah.
Terms.
Yeah. I don't want to have decompositions where I like wrote a degree 1 million polynomial and then subtracted it off from itself. Yeah. Okay, so the point is that this is going to be our idea of what it means to express a polynomial in terms of other polynomials. But we still need to figure out what we mean by having no special distributional properties. So here we say that a sequence of polynomials, q1 through qm, all polynomials from Rn to R, we say that this is an epsilon comma n diffuse set if the following two properties hold. First off, they should all be normalized. Qi should have L2 norm at most 1 for all I. Secondly, we want it to be the case that for any vector a1 through am of elements of R, then if we think of all of these polynomials as sort of, if we evaluate all of these polynomials simultaneously at the same random Gaussian, we want the probability that qi is with an epsilon of ai for all I to be at most n times epsilon to the m.
It's the anti-concentration of some n cube.
Yeah, basically. So the point here is that we sort of think of this sequence of polynomials as a single vector-valued polynomial. Then we want to say that the probability that when we evaluated a random Gaussian, that we lie in any epsilon-sided cube should be small. In fact, it should be not much more than the volume of the cube. So what this says is that, in fact, sort of our heuristic for how good anti-concentration should be is more or less correct up to this factor of n, at least when we only consider it on scales of order epsilon. Now, it could, of course, be much worse anti-concentrated if we look on sort of much smaller scales, but scales of order epsilon were okay. I mean, n is sort of the bound. So
I understand, but what will it be
in the cases that we're looking at, n will be some arbitrarily, will be epsilon to the minus c. for some arbitrarily small c.
So basically, you're saying that not only is each qi very well anti-concentrated, but they're also behaving independently of one.
They're behaving close to independently. At least when
That's morally what.
yeah,
Density.
morally their joint distribution is bounded density. Yes.
Bounded density.
Yep. Yep. Okay, so sort of we had our idea of expressing in terms of other polynomials. This was our idea of no special distributional properties, so we put them together. We said that an epsilon n diffuse decomposition of size m of a polynomial p is a decomposition of p such that the q1 through qm that we have form an epsilon comma n diffuse set. So we can express it in terms of polynomials that have no special distributional properties. Okay, so we have these definitions. They wouldn't be very useful without the following theorem, which says that we actually have these decompositions. So the point is, if we have epsilon, c, and n bigger than 0 as parameters, this n is actually different from the other n. If we have p of x any degree d polynomial, then there exists well, p might not have a diffuse decomposition, but there exists a p naught that's very close to p. It's within epsilon to the n of p, roughly, such that p naught has an epsilon comma epsilon to the minus c diffuse decomposition of essentially constant size. So this is sort of a structure theorem. It says that up to small error, we can write our polynomial as an actual composition of sort of a structured part. This is like an h where it depends on only sort of a bounded number of variables, with sort of a random part, this diffuse set of polynomials. Now, one thing to note here is that some of these constants that I've sloughed under the rug are kind of big. These O of 1 terms actually are like Ackermann of D. Now, this is, I think, just an artifact of my proof. I think that these terms should actually, you should be able to get away with polynomial bounds, but there's a big discrepancy there, and I don't know how to bridge it. In any case, the proof of this theorem is very technical. I don't have anywhere near the time to go over it, so I'll give only a very brief sketch. The idea here is we're going to start with a sort of the trivial decomposition of our polynomial. P is the identity composed with P. And we're going to iteratively refine this to somehow get better and better decompositions until eventually we have the one that we want. So the main step here is we want to show that if we have a decomposition into Q1 through Qm, and this is not an epsilon comma epsilon to the minus c diffuse set, then one of these Qi's can be decomposed further. In particular, it can be decomposed into a sum of the following: a linear combination of the Qj's of the same degree, Qj's from the same set, a bounded number of products of lower degree polynomials, and a small error term. And eventually, when we have sort of our error terms become too small, we can just throw them away. The lower degree are completely new polynomials. And so the point here is that we sort of iteratively keep applying this and getting sort of better and better approximations. But it turns out that there's an ordinal number monovariant that sort of keeps track of the number of Qi's of each of the degrees that actually shows that this process has to terminate. So eventually, we end up with this diffuse decomposition that we want. So it's an ordinal number. Do you know what those are? Okay, but I mean, ordinal numbers are like, think of them as polynomials in a variable omega, where the coefficients have to be non-negative integers. They have the obvious ordering on them. And there's the property, though, that there's no infinitely decreasing sequence of ordinal numbers. So if you have an ordinal monovariant, it means that essentially it has to terminate after some finite number of steps. And that's how we show termination. It doesn't depend on the axiom of choice. And in fact, if you start with an ordinal number of size about omega to the d and sort of bound the complexity of the things that you get in terms of the number of steps that you've taken, you can put explicit bounds on how many steps this takes, and it turns out to be about Ackermann of d. And so that's sort of where these terrible, terrible bounds that we have are coming from. Any other questions about this?
Can you just say some intuition first?
Some intuition. That's a little bit hard. So the first point is that if these things are anti-concentrated, well, so I've got a high probability of ending up at 0. Let's see. That's not such a good idea. No, sort of the best intuition I think I can give for it is that sort of, when we were back looking at these polynomials that had poor anti-concentration, the only way we could cook them up was by having them be compositions of other things. And
The assumption in step 2 is not that it doesn't have anti-concentration. It's that it doesn't have this decomposition. It's not diffuse.
no, so we have a set of polynomials that's not diffuse. What that means is that there is some point. Yeah. 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 So I mean, yep. The proof is pretty technical. It involves looking at sort of the derivatives of these polynomials, showing that if there's some appropriate linear combination of these guys such that.
Let me ask you a simple question, which maybe
Yeah.
help answer. Suppose we have just two polynomials
Mm-hmm.
that are not diffuse.
Uh-huh.
Can we see why? So you may.
I mean, even with
Same answer, but
even with one, it's somewhat difficult. But the point is that there's a good version of anti-concentration that's not hard to prove that says a polynomial has small probability of being much smaller than the size of its derivative. And therefore, you can show that if your polynomial is not well anti-concentrated, it has a reasonable probability of its derivative being small. And its derivative is an entire vector-valued thing. And so having this entire vector-valued thing being very small is actually a very powerful condition.
that's
Yes.
the result of the new polynomials, the derivatives of the original polynomial. That's the low degree.
They're effectively constructed by taking sort of random derivatives of the new polynomials. The construction of the decomposition is very randomized given the proof, but the idea is that if you've got large powers of some polynomial, if you take random derivatives of the polynomial, you expect to get out copies of that polynomial that you're taking large powers of with reasonable probability.
It seems to me morally, you're saying if there's a small area of big probability,
Uh-huh.
then in this area, the density is the Jacobian of the polynomial. You do a variable. So the
Yeah.
Jacobian must be big.
Yeah.
And then you get that some derivatives are big.
You think you've got it backwards, but yeah, you showed that some derivatives are small.
Okay, it's 1 over the Jacobian.
Yeah.
Some derivatives are small.
Yep.
And then you want to leverage the fact that it's a polynomial.
Yes.
Because it's not a general function, that if some derivatives are small, you get some structure.
Yes.
Is that the...
Yes, that's the basic idea.
So it's all, the whole story from the beginning is very, reminiscent of the situation where, over finite fields and the decompositions that is done.
Yeah.
So, I'm just wondering, so morally I'm sure it's the same, technically I'm sure it's very different, but
Mm-hmm.
you have like clear places where, where it differs, like when you do this,
Mhm.
Green Tau or Lovett,
Yeah.
Kaufman and all these decompositions,
Uh-huh.
of course they are using, they build such decompositions from
Yep.
derivatives, directional derivatives
Yep.
of the polynomials that were
Yep. I mean, I think that the actual constructions are pretty different. I mean, their constructions are somewhat more combinatorial. Again, they're still looking at the same sorts of derivatives and things, but they need to use combinatorial arguments to make things work. Here I use very probabilistic arguments to get things to work. I also have this notion of errors that they don't have. I mean, because of course, one way that you can still be poorly anti-concentrated is you have a poorly anti-concentrated polynomial, and you just add anything that's small with high probability to that. And so somehow I can't do anything quite as clean because I have to somehow have something that notices the fact that I've got small errors that I can throw out.
Oh, no, that's
Yeah.
good also there.
Yeah.
You add
Yeah.
low end to error.
Yep. Yeah. It's somewhat similar. I haven't really understood their arguments well enough to find out if there's some sort of deeper analogy between techniques?
Would be nice.
What do you think is very intuitive? There's a
No,
formula
of
for
course,
the density,
I know,
and the formula involves the derivatives, and it's a polynomial. So
But
Yeah.
it's not clear that when you write, how to write it as a combination of the lower degree polynomials with the derivative.
no, but
So you still want it approximating the original one.
yeah. So you know that this Jacobian is very 1 over the Jacobian is very very big on a big
Mhm.
region of this small block.
Yep.
So it means that there is a big region where after all it's a polynomial. Okay?
Yeah.
But the derivatives are in a big region tiny. Okay, so that means that there is some simplification happening.
Yeah.
That's all. But of course you need to make it. I agree with you in
Yeah,
but it's
Yeah.
intuitive that something like that should happen.
Yeah.
And it's even like, in some sense I think more clear than the finite field case. That's a matter of taste. Okay.
Yeah.
So you said before that the ground you really have is this argument in the various
Yep.
parameters, but you think that in reality you think it's actually just going to be polynomial?
Yeah.
Do you have intuition why it should be polynomial, or is it just sort of
I've got some intuition. Well, first off, I've actually worked this out for degrees 1 and 2. It is polynomial for degrees 1 and 2. Then again, I mean, the argument depends on D. So secondly, though, okay, so secondly, there's just the I've not found a counterexample yet. But thirdly, I feel like what's actually going on is something very algebraic. I have a few polynomials, and I'm somehow constructing something out of taking large powers of them. And I feel like if you should have actually understood sort of the algebraic constraints that were necessary on forcing something to have poor anti-concentration, then somehow polynomial feels like the right way of making these constructions work. Of course, the point is that I feel like what's fundamentally going on here is something algebraic, but my proofs are all very analytic and probabilistic and involve sort of these terrible recursions that somehow don't fit into the same framework. Any more questions on this?
Okay, just something about the last thing you said. I mean, how can it be algebraic? The notion of diffusion itself is about.
Yeah. I mean,
thinking about.
it's not sort of strictly algebraic. I mean, it's somehow some approximate algebraic. Like, we're finding these polynomials that are sort of approximately within large powers of an ideal. Now, I do think that you can get something honestly algebraic if you somehow talk about this sort of thing as epsilon goes to 0. Like, I think the only way you should fail to be somehow actually infinitesimally and poorly anti-concentrated is if you honestly have a decomposition into lower degree polynomials with some additional properties. I mean, just saying that you're x squared plus y squared plus z squared if x, y, and z are, say, linear polynomials isn't actually enough to make you infinitesimally poorly anti-concentrated. But, I mean, somehow I feel like being infinitesimally anti-concentrated should honestly be an algebraic property.
What about some kind of point where
Yes, I mean, it's going to relate. Yes. I mean, that should give you some constraint on the Jacobian vanishing on some sort of set. But I have not actually been able to work this out fully.
For example, the finite field case is not really a finite field case because they are working with real complex values because they put the finite field polynomial in the exponent of some root of unity. Right? That's why they also have a 12 and so on. But it's not. I don't think it's that far. I'm sure it's far, but I don't think it's that far. Maybe there are. And also they get big bounds, but not as bad as I can have.
Yeah.
So, I mean, at worst, it's a tower.
Yeah.
Which I don't know, it's a big relief, but I think it's worthwhile looking at.
Okay, maybe I should check that. Maybe I should check those out
Or
again.
you should just talk to Shah. If you and Shachar met, I think that you can in a couple of hours agree on the common and different aspects.
Okay. Well, anyway, so we have this theorem. How might we sort of use these ideas to give ourselves a better replacement method? So again, like, suppose we're trying to, prove an invariance principle. We have f of x is sine of p of x, p a degree d polynomial, normalized to have variance 1. And the key difference is that we're going to come up with this smooth approximation G using these ideas rather than just this simple row of P of x. So the point is, first we can obtain a P naught that's very close to P, such that P naught has an eta to the minus c diffuse decomposition. And the point is that f of x is sine of P of x, which is approximately sine of P naught of x. That is equal to sine of h of q1 of x through qm of x, and we're going to approximate that by some rho of q1 of x through qm of x. Where here, rho is some function on Rm, such that rho of q1 through qm should be equal to sine of h of q1 through qm, well, as long as we're not close to the boundary. As long as this vector q1 through qm is more than distance eta from the boundary between the +1 and -1 regions of this other function. So let's see what happens here with our approximation error, because that's where we hope to get the major gains from. The point is that because P and P naught are very close, it's not hard to show using concentration and anti-concentration results that probably the sine of P of x and the sine of P naught of x are the same. Now, the main error that we have to look at is the difference between sine of h of q1 through qm and rho of q1 through qm. Now, of course, this is roughly going to be the probability that our vector q1 through qm lies within eta of some 0 of the polynomial h. Now, intuitively, we have this hypersurface defined by the polynomial. We want to say what's the probability we're within distance eta of that. That's some region of volume eta. By the diffuse property, the probability of lying in this region of volume eta shouldn't be too much more than eta. Now, to make this rigorous, of course, what we try and do is we try and cover this region in eta-sided boxes and just add up count the number of boxes, use the diffuse property to bound the probability of lying in each individual one. Of course, we can't do that straight up because this region isn't bounded and thus can't be covered in finitely many boxes. So the first thing that we will do is we can show that by pretty standard results that qi of x is less than polylog eta for all I with high probability. Then once we've restricted ourselves to this finite region, we can then cover it with these eta-sided boxes and use the diffuse property to actually get a count. It takes a little bit of work to actually get a bound on the volume of this region, but it's not too bad. And so we have an approximation error that's on the order of eta to the 1 minus c, after hiding some polylog factors. So we then need to deal with the replacement error. The replacement error depends on the sort of size of the kth derivatives of things. Now, because we defined rho to sort of vary over this distance of order eta, it can be the case that we can construct rho such that any kth order partial derivative is on the order of eta to the minus k. So, assuming that the first k moments agree, we care about sort of the first k derivatives, or k plus 1 derivatives. So the replacement error depends on the kth order partial derivatives of g of x with respect to each of the coordinates, and we rewrite this using the chain rule, and we get something that depends on, well, eta to the minus k from these kth partial derivatives of rho times the kth powers of the partial derivatives, but now not of our polynomial p, but of these polynomials q. And so the point is that this diffuse replacement method, the error is going to depend on powers of the partial derivatives of q rather than powers of the partial derivatives of p. Now, this is actually a good thing, because if we depended only on the partial derivatives of p, we'd be writing our error in terms of this same regularity parameter. And of course, we know that just using the standard notion of regularity, you can't do better than tau to the 1 over d. So, but this does mean we're going to need to invent a new notion of regularity. And for our context, the correct notion is roughly the following. If p is a degree d multilinear polynomial, we say that it has a tau n m epsilon regular decomposition if there exists a p naught that's within epsilon of p, basically, such that p naught has a tau n diffuse decomposition of size m, such that in addition, these qi's that we're decomposing into are, first off, they're multilinear, and secondly, all of their influences are at most tau. So they're all multilinear and tau regular. And so from this, using exactly the techniques described for the replacement method, we get that if P is a degree D multilinear polynomial with a tau n m epsilon regular decomposition, the CDF distance between P of a Bernoulli and P of a Gaussian is the following mess. But it should be noted that sort of the main term here is basically a tau to the 1/5 times n. And this should be compared to the sort of tau to the 1 over 8d that we saw before. And so so for d moderately large, this becomes a tremendous improvement over what we had, at least just in terms of the tau dependence. So one way to note to see that this actually is sort of looking at the right thing is to look at this bad case that we had for the original invariance principle. We've got P of x is tau times x naught plus this other linear term to the d. This thing has a beautiful diffuse decomposition. P of x is tau times q1 plus q2 of x to the d, where q1 and q2 are the obvious polynomials. Now, of course, q2 of x is highly regular, but q1 is not remotely regular. And so somehow, by looking at these regular decompositions, we've sort of pinned down exactly that the variable x naught is sort of the one responsible for our invariance problems. And we've done this by sort of separating out these two different parts of the polynomial by sort of detecting this anticoncentration. Okay, now, of course, in order for this invariance principle to work, we need to have regular decompositions. And since it wasn't obvious originally that diffuse decompositions existed, it's not clear that regular decompositions exist. This would be pretty useless without a regularity lemma, which fortunately we have. Again, we fixed some parameters tau, c, and m. We have a degree d multilinear polynomial p that we want to evaluate at Bernoulli inputs. What we can do is we can write it as a decision tree of depth about tau inverse, such that with probability 1 minus tau over a random leaf, the resulting polynomial is either, well, its variance is much smaller than its squared L2 norm, i.e. it's constant up to a small relative error, or it has a tau to the minus c, O of 1, O of tau to the m, regular decomposition.
So can you write the last term is what?
This last term is the epsilon. So it's sort of the error between p and p naught. And the third term is the size of the decomposition. So tau is the scale, and tau to the minus epsilon is the tau is the size of these cubes that we're looking over, and tau to the epsilon is the sort of bound on the PDF at these scales. Yeah, tau to the minus c. Yep.
Which one was capital N?
Capital N is this tau to the minus c. Okay, so we have this. The proof of the regularity lemma, basically we have to sort of redo the proof of the original decomposition theorem. Just sort of at every step, we have to maybe fix a bunch of coordinates and readjust things a little bit to make sure that all of these polynomials that we're decomposing into are regular. That's what I just said. Okay, so the point here is that now when we combine the diffuse versions of the invariance principle and the regularity lemma together, we find that you have your polynomial you want to evaluate at random Bernoulli. You can write it as a decision tree of depth about tau inverse, and with probability 1 minus tau, your leaves are either nearly constant or within about tau to the 1/5 minus c of their corresponding distance of a polynomial of Gaussians. And so note that this statement with the classical versions of these theorems was exactly the same, except we had an O of tau to the 1 over 8d. And so we have a major improvement in this exponent, which for a number of applications gives us sort of qualitatively better results.
Yeah, I'm just wondering whether the Ackermann dependence on the D. So what's the trade-off there? So you improve, definitely improve.
Yeah.
You have a constant in the exponent
Yeah.
of tau.
Yeah.
But the constant factor in front of it is
The
Ackermann.
constant up front is Ackermann. So what this means in practice is that we get sort of we get asymptotically better results if you honestly fix d at something. I mean, you pick some moderately large d, but then you fix it and let whatever other parameters you're looking at go to 0 or infinity.
So this would be another way of saying it is that this is meaningful if tau is inverse factor 1 and d.
Yeah, something like that.
It will be exponential. Yeah.
Yeah.
But then it would do worse thoughts or much smaller.
Okay. So, well, there are a bunch of applications of this, but one that's sort of maybe the best motivated is the one to noise sensitivity. So the idea here is that if you have a Boolean function f, the noise sensitivity of f is sort of a measure of the sensitivity of the output of f to small changes in the input. So there are a number of different... yeah. Yes. This sort of thing. For the noise sensitivity. For what are you talking? Yeah. Yes. 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 Here. Yes. 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 This is already the best known for quadratic. Yeah. Okay. So, blah, blah, blah. Noise sensitivity. I mean, okay. This measures the sensitivity of the output to small changes in the input. There are a number of different measures of noise sensitivity. We'll talk about two of them here. First off, there's a Bernoulli notion. You have some function from Rn to plus minus 1. It's a Boolean function. You have some parameter delta between 0 and 1. We define the noise sensitivity of f with parameter delta to be the probability that f of a is not equal to f of b. Here, a and b are random Bernoullis, but they're not independent of each other. You can think of them as you first select a randomly, and then you get b from a by randomly and independently flipping the sign of each coordinate with probability delta. So this is basically the probability that on two random inputs that differ on a delta fraction of their coordinates, that you have different values of your function. There's also a Gaussian notion. Again, you've got some function from Rn to plus minus 1 and a parameter delta. The Gaussian noise sensitivity of f with parameter delta is the probability that f of x is not equal to f of y. Here, x and y are Gaussian random variables. But sort of the way that you make a noisy version of a Gaussian random variable is slightly different. You build them such that together they're a joint Gaussian random variable with the following covariances. And in particular, sort of x and y have covariance 1 minus delta, essentially. So this is sort of the probability that a pair of 1 minus delta correlated Gaussians give you the same value, or give you different values, I guess. So the basic problem that gets looked at here is if f is a degree d polynomial threshold function, we'd like to find upper bounds on the noise sensitivity of f with parameter delta and the Gaussian noise sensitivity of f with parameter delta in terms of d and delta. And so the generally believed answer to this question, at least is given by this conjecture of Gaussian and lineal via some reductions of Harsha, Kilvins, and Mecca, which says that if you and it would say that if you have a degree d polynomial threshold function and a parameter delta, then the noise sensitivity and Gaussian noise sensitivity should both be O of d root delta. And furthermore, if this conjecture holds, it'll be tight as long as as long as delta is small. So one thing to note before we move on is there's actually a reasonably close relationship between the noise sensitivity of f with parameter delta and the Gaussian noise sensitivity with parameter 2 delta. And the way to see this is that when you're defining the noise sensitivity, you look at these pairs a, b, and looking at the Gaussian noise sensitivity, you look at these pairs x, y. Now, when you pick those parameters, these things agree to all of their first three moments. And what this suggests is that using an appropriate invariance principle, you should be able to show that for regular polynomials f, that the noise sensitivity of f with parameter delta is roughly the Gaussian noise sensitivity with parameter 2 delta. Okay, so what's known? Gaussian lineal has been known for a long time for degree 1, but for degree more than 1, it took a while until basically anything non-trivial could be said. Basically, these first non-trivial bounds were proven by sort of these two groups at basically the same time in 2009. And the point was that if you have a polynomial of Gaussians or a regular polynomial of Bernoullis, you could show that for an appropriate parameter t, that p of x would be bigger than t, which would be bigger than the absolute value of p of x minus p of y with high probability. And the point is that now if you want to look at a general polynomial of Bernoulli's, you reduce it to the regular case using a regularity lemma. And putting these together, you prove the following bounds on the noise sensitivity and the Gaussian noise sensitivity. And so you get bounds that are sort of on the order of delta to the 1 over some constant times d. And these were nice. I mean, these are bounds. They go to 0 with delta. They're non-trivial. On the other hand, the expected answer is delta to the 1/2. And the trivial bound is delta to the 0. So these are, in some sense, only a slight improvement, at least for large degree, over the trivial bound. Now, a year later, I had an argument that actually gives the optimal bound in the Gaussian case, O of d root delta. But this bound sort of, it's a short proof, but it has some problems with it. It depends sort of very critically on symmetries of the Gaussian distribution that just simply don't exist in the Bernoulli case. And this means that sort of generalizing this argument to the Bernoulli case directly is effectively impossible because the symmetries that we depend on just don't exist. Furthermore, we could try using the invariance principle to take this bound in the Gaussian case and get a bound in the Bernoulli case. Unfortunately, due to this sort of tau to the 1 over d type dependence that we have, it's not hard to see that these techniques won't give you a better bound than delta to the 1 over O of d again for the Bernoulli case. But on the other hand, this new invariance principle can actually do better than this. So the basic ideas of the argument is the following. We first prove a bound for regular PTFs. We show that if your f is sine of p of x is a PTF of a degree d polynomial with a tau m nm epsilon regular decomposition, the noise sensitivity is at most the following mess. But I mean, the point here is we show that the noise sensitivity of f is roughly the Gaussian noise sensitivity, which is O of d root delta. So we have that O of d root delta plus the error term that we got from applying our invariance principle, and that's our bound. So the next thing to do is we want to get a bound for general PTF, so we can get a bound that's O of delta to the 1/6 minus an arbitrarily small constant. And the point here is that we want to use our regularity lemma to reduce to the regular case. So we write f as a decision tree of depth about delta to the minus 5/6. Now we note that since a and b agree on all but a delta fraction of their coordinates, there's a probability of 1 minus about delta to the 1/6 that they agree on all of the coordinates defining the path down the decision tree that we happen to take. Now, if they disagree on this path, we're not going to say anything useful about what's going on. But if they do agree on this path, then we just need to know that, well, we've got this resulting polynomial corresponding to that leaf, and we need to look at the probability that that polynomial differs on a and b. So we need to look at the noise sensitivity of the leaf now. Now, with probability 1 minus delta to the 5/6, this leaf either has constant sign with high probability, and in that case we're in great shape because the sign of p of a and the sign of p of b are both this constant with high probability, or this p sub rho has a regular decomposition, in which case we've reduced to the regular case. So in either case, f of a is equal to f of b with a probability 1 minus O of delta to the 1/6 minus c. And so that gives this result. So in conclusion, we presented here sort of the basic theory of diffuse decompositions and, well, one of the applications. These ideas are less new than they were when I first wrote these slides, but there are still several areas for potential improvement. Well, a couple notable ones. Firstly, the d-dependence on the size of these things is still absolutely terrible. It would be really nice if we could make it, say, polynomial or even exponential, because then any of the results that depend on this theory will have not terrible dependence on their degree. Secondly, and maybe even more importantly, I know of a few applications of this to the noise sensitivity, to certain pseudo-random generators, and so on. But it feels like this is sort of a pretty useful way of thinking about polynomials in many variables. And it feels like there should be more applications. I just don't know what they are. So if you can find new applications, that might be even better, especially because it leads to more papers. In any case, this work was done with the support of an NSF postdoctoral research fellowship. That's all I had to say. Are there any questions?